All right, so we're going to find this derivative two different ways. So the first way, using the product rule, we can write any power of a function, like 2x plus 5 squared, as the product of 2 or more. So in this case, it's 2x plus 5 to the power 2. Well, that's just 2x plus 5 times 2x plus 5. And then you guys could differentiate that using the product rule from last day. Differentiate the first, leave the second, plus leave the first, and differentiate the second. I'll put the 2 in brackets on the end. Some people prefer to differentiate the first, leave the second, and then differentiate the second and leave the first. But so just basically flip flop the order I have things in here, and that's totally fine. Personal preference. I think in the video lesson, without even thinking about it, I switched at least one time, but ultimately it doesn't matter. Just differentiate one at a time. And that's the derivative. But this one's not too hard for us to clean up, so let's just do that. You could probably do this in one step. I'll do it in 2 steps. So what's that? 4x plus 10 and another 4x plus 10. So the derivative, 8x plus 20. So using the product rule, we can find derivatives of powers, at least the power of 2. Let's do this another way since we have the space and the time. If this was you several days ago, then you would have taken this farther and expanded everything out all the way. So the original function, if you multiply 2x plus 5 times itself, you get 4x squared. You get 10x plus 10x, that's 20x. And then 5 times 5 is 25. And you could differentiate it just using the power rule and those basic derivative rules we did on our the first day we learned derivative rules. So 8x plus 20. You get the same derivative. I would argue probably just expand using either, if I had to choose between either of these two rules, I'd probably pick the second one because it's not too hard to expand. But you guys, hopefully you're convinced they both work. I'm going to show you guys a third way we could have done that. Because what if I asked you to find the derivative of 2x plus 5 to the power of 10? It's technically possible using the second method here. You do have the skills to expand 2x plus 5 to the power of 10. It wouldn't be fun, but you guys could do it. It might take you 20 minutes, and you might make some mistakes on the way. I would make mistakes along the way. So can we develop a rule that will help us do any power function? And the answer is yes, because otherwise, what would be the point of what we're doing? To start off, I'm going to show you guys the product rule when you have 3 functions. It's kind of an extension of the product rule, and then you could extend this to 4 or 5 or 6, but we'll just do it for 3. So here it is for you guys. If f of x equals the product of 3 functions, then, and I'm going to squeeze this in down below, the derivative of this product of 3 functions, you kind of do the same thing you did with the product rule for 2. You just differentiate one at a time, and you leave the other guys alone. So you would differentiate p, so p prime, but then you would leave q, and you would leave r alone, q of x, r of x. So just differentiate one at a time. And then you just take the sum of all those kind of triple products. So for the second term here, you would leave p alone, and this time you differentiate q. And then leave r alone. And then lastly, you would leave the first 2 alone, p and q, and you would differentiate r. Just a natural extension. And so if we were to do a product rule for 4, you would just differentiate one at a time, and you'd have 4 things to add. But we'd be kind of losing the plot a little bit. But let's give this rule a spin with not too crazy of a cubic function here. We're going to do this one 2 ways, like the first question. We're going to use this extended product rule, and then we're going to check it using the skills we might have done from a few days ago, where we simplify it first, because this one's not too bad to expand. So here we go. What is the derivative here? I'll use Leibniz notation, dy by dx, just because. But I'm not your dad. You can use whatever notation you want. Dy by dx. All right, so we differentiate the first function, x. The derivative of x is 1. And then you leave the other two guys alone, x plus 1, x plus 2. And then you leave the first one alone, x. You differentiate the second one. The second one is x plus 1. And the derivative of x plus 1 is also 1 times x plus 2. I'm trying my best to use my fine motor skills, but I might be bleeding into the second half of the page here. And then for the third, we leave the first two and differentiate the last one. X times x plus 1, and the derivative of x plus 2 is 1. You guys okay with that? It's just kind of differentiate one thing at a time. And that's the derivative. Now, here, cleaning this up is not too bad. It's just a bit of expanding, like from grade 10. So like this first bit would just be x plus 1 times x plus 2. That'd be x squared. 2x and 1x would make 3x. 1 times 2 is 2. I might just, if I'm not going to show that step, I might just visualize that I'm just using the distributive law here and just cleaning things up. And then what do we have? We have x times x plus 2. So x squared plus 2x. And then we have x times x plus 1. So that's x squared plus x. And then we'll collect like terms. X squared, x squared, x squared, that's 3x squared. 3x and 2x is 5x. I should go back to grade 9 here just to make sure. I'm going to underline my like terms just so I don't miss anything. I do this question once a year. 3x plus 2x is 5x. I missed an x. 6x. And you guys all just sat there in silence and you just let me make my own mistakes. Okay. And then plus 2. Are we good? Is that good? Okay, somebody nodded. All right, now I don't need to. I asked you guys if that was good. We can. I didn't really need to. We could check our answer, and since we have the time and the space, let's check our answer by simplifying first. So if I were to take the original function, and let's do x plus 1 times x plus 2. That would be x squared. 1x and 2x is 3x. 1 times 2 is 2. I'm just expanding the first one. This is what you guys would have done a few days ago. And arguably, it's still a good method because it's not too bad. It doesn't take too long. Algebra is not too tricky. X times 3x plus 3x squared, and x times 2x is 2x. So if this this extended product rule isn't full of crap, then we should get the same derivative. And just to be different, I'll use prime notation here. So y prime equals, bring down the 3, 3x squared, bring down the 2, multiply it by 3 plus 6x, and the derivative of 2x is 2. And yes, it's all the same, right? As it should. So are you guys convinced this extended product rule works? You got it in the toolbox now. You can use this for 3 functions. You can use this for 4 functions. But if it's not too much work to simplify first, that works too. The idea here right now, you guys have several different methods that work depending on the function and what skills you have. All right. So at this point, we're going to start using the product rule from yesterday and this extended product rule to see if we can see a pattern and then use that pattern to get a rule for what happens for higher powers, not just 2, not just 3. We're going to start small. We're going to start thinking about a generic function. I'll call it h, and it's the square of a function g. We're going to use the product rule to get a general rule for this derivative. So here we go. So what would be, if we were up above, what did we do? We wrote that function squared. We just wrote it as that function times itself. So let's write g of x squared as g of x times g of x. And then that's a product of two functions. So we can find the derivative using our skills from last day. So what would we do? We differentiate the first, g prime, and leave the second, g, and then plus, and then we would leave the first alone, g, and we would differentiate the second, g prime. And if you guys remember back in grade 9 in your collecting like terms lesson, where the teacher was like, hey, are these like terms, u, v, and vu? And like somebody like, no, but then the trick was like, yes, they are like terms because order of multiplication doesn't matter. These are like terms, so we can actually add these together. We get two of them. And I'm going to choose a specific order here. It wouldn't really matter. But we get 2. I guess that equal sign is just purple. We get 2 times g of x times g prime at x, because those two terms are really the same thing. And look at us. We have actually developed another rule. This is a rule for taking the derivative of a function squared. You bring down the 2. You leave the inside alone, g at x, and then you multiply by the derivative of g prime. You guys okay with that? Let's do it with g of x cubed, because we learned a product rule for the product of 3 functions. So let's apply that extended product rule, and let's see if we're going to get something different. Let's see if we can generate a pattern based on what we get. So we're going to write, this time our function h is a function to the power of 3. So I can write that function, that's just g at x times itself 3 times. Okay, and we have a rule for this. So take the derivative, we just basically differentiate one thing at a time. So g prime at x times g at x times g at x, and we just differentiate like the first one, then the middle one, then the last one. If you suck at printing, you're getting lots of practice with your g's and your x's. My 8-year-old could use this exercise for sure, because he sucks at printing if he didn't follow that. All right, and guys, aren't those all just like terms as well? Each of those terms has a g, another g, and a g prime. So I can actually collect them all together, and we're going to write it in a very specific way here. So there is 3 of those terms, and again, I'm going to be very specific how I write this. Each of those terms has 2 g of x's. G of x times g of x, I can write that as g of x squared. I'm going to do it like this with some square brackets just to keep everything sorted. That just means g at x times itself. And each of those terms is also multiplied by the derivative, g prime at x. Look, there is a pattern emerging here. So this was g at x cubed. We brought down to 3. We left the inside alone. We took 1 off the exponent. Kind of looks familiar, right? Except with this new additional twist, we multiply by the derivative on the end. I think that you guys could predict the rule for g at x to the power of 4. I didn't give you a ton of space. Can you tuck in a prediction up at the top here? Anybody want to share what their prediction is for the rule for a function to the power of 4? Sane, what do you think?
4 g of x cubed times g prime x.
Yep, you got it. Yeah, we don't need to, at this point, the pattern has kind of shown its head, and we don't need to do the power rule for product rule for 4 functions. You're exactly right. Bring down the 4, leave the g, take 1 off the exponent, which is fantastic because you guys are already used to doing this rule basically. It's just when it's the power of a function, we have this additional multiply by the derivative of that inner function. So let's generalize what we've done here. This is the power of a function rule, and it says this. So if you have a function that is some other function raised to some power, and it doesn't matter what power. We looked at positive integers. This works with negative integers. It works with decimals, fractions, what have you. Then h prime is equal to, so you bring down the n, you leave the inner function alone, you leave it alone, you take 1 off the exponent. Again, you guys are used to doing this. And then you multiply by the derivative of what's on the inside. And I think that's kind of neat. We just proved this by just using the product rule from yesterday. So things are ramping up quickly, but they're ramping up in a nice natural way where it just feels good. Going back to the motivation problem, you guys now have a quick and efficient way to take the derivative of 2x plus 5 to the power of 10. That does not require you to expand that all the way. I shall do it with you. Actually, you know what? I'm going to do my attendance, and you guys are going to do it, and then I'm going to come on back for the ride. I'm going to pause the recording. All right, and we're back. So I'm going to play catch-up here. Let's see how you guys did. So the rule says, bring down the 10. Leave the inside alone, 2x plus 5. Take 1 off the exponent, 9. So just like our power rule, this time the power rule function says you have to multiply by the derivative of what's on the inside, which is just 2. Did you guys get that as well, hopefully? Now, this one is pretty easy to clean up. 2 times 10 is 20. Oh, this is a good talking point. No, we can't just distribute the 20 into the brackets there. You would have to distribute 20 to the power of 9, which is really, really, really big. So would not advise doing that. I'm not your dad, do what you want, but this is fine. But yes, we cannot just put the 20 inside a bracket to the power of 9. You can't do that. I don't know why I have so much space for these. I assume you guys have already tried B. I guess I'm using deep purple now. That's fine. Somebody who hasn't helped out yet today, can you just give me the first step of this derivative? All right, keep going.
5x squared plus 3x minus 1.
Leave the inside.
To the power of 6.
Yes.
Times 10x plus 3.
Perfect. Excellent. Yeah, that's very good. And this is basically nice and factored. There's nothing else that I would do here. The derivative is fully simplified. I think some of you guys might need this, just need this note. Hopefully this is another purpose of the warm-up. Like, do not expand this. It is an exercise in futility. There is really no good reason for you to expand something to the power of 6. Just don't do it. Like, it's actually counterproductive. Most of our applications of derivatives will be asking what makes the derivative 0, and you'd like things to be factored as much as possible doing that. So don't expand. Resist the urge. I mean, like 99% of the time, don't expand. All right. What C? We didn't do things like C. We didn't do radicals today. But you guys know, because you guys took grade 11 math, you guys know that you can write the root of 5x minus 3 as a power. That is 5x minus 3 to the power of a half. And then we can use our new power of a function rule. It's applicable in so many different areas. I'll find the derivative with you guys here. Let's just to be different, let's use Leibniz notation, dy by dx. And I'm the one teaching, so I'm talking here, and you can hear my mantra as I find my derivative. But this is something you guys can just talk through in your own head. Bring down the 1/2, leave the inside alone, take 1 away from the exponent, -1/2, and then multiply by the derivative of what's on the inside, which was 5x minus 3, so we multiply by 5. And that's our derivative. We'll clean it up. We don't like negative exponents, so this would be, we have 5 on top, all over 2, 5x minus 3 to the power of 1/2, which is totally fine. We've had this conversation like at least 6 times so far this year. This is fine, but also if the original question was given as a radical, you're probably going to see your answer as a radical in whatever resource you're using. So we'll do it too. How'd I do? Did I do okay? Does that make sense? You guys were feeling good? I'll trust that you guys will ask a question if you have a question. All right, and the last example to do is one where we have a rational function, but now we have the skills to do this. We can write this as a power. This is x plus 1 to the power of -2. And then we can use our new rule. I'll slip back into prime notation. I'm just trying to get you guys used to seeing all the different notations here, there, everywhere. It's just personal preference. You go to Waterloo, they'll have the notation they like. You go to York, they'll have the notation they like. So it's just personal preference, really. Okay, so what do we do? Bring down the -2. Leave the inside alone. Take 1 away from the exponent. Time travel back to grade 9. We're playing Find the Markers and Roblox. And you guys know when we take 1 away from -2, it's -3. It's not -1. And then multiply by the derivative of what's on the inside, which I guess you could have got away without doing because it's just 1. This is the derivative. Nothing wrong with it. However, we do like to write things with positive powers. This would be -2 over x plus 1 cubed. Look at us. Look at all the derivatives we've done. Remember last week we were doing first principles, right? And now we're doing all these complex derivatives, and then it's just going to continue. We're just going to be able to do more and more. It's great. Anything you guys want to chat about? I've kind of covered all the different types of functions you might see. Minus just making some really, really complicated ones. But yeah, I feel like any more is kind of redundant. You guys just need time to practice now. The practice for today is from the same handout as yesterday. So I don't need to give you guys, unless you didn't get it, but I think I gave everyone that the previous day. So when you're doing these problems, if it's a power of a function, try using the new rule. You could also give that formative quiz a try. And if you didn't do the other one, maybe you could try that one too. They're just free marks, basically. They can't hurt your mark. But yeah, just to, like when it's June, I'm not going to go back and see if you did the formative quiz power of function rule. Like that's something you would do like today or tonight. And then I would see if you did it and record your mark. But just to be clear, formative means can't hurt your mark. All right, 36 minutes of practice time. I'll end the recording.